everybody, the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. Bam! So today we are talking about Gibbs Free Energy calculation number 3. Alright, so let's get moving on that. We're going to determine the delta G naught, that's Gibbs Free Energy, for the combustion of 1 mole of acetylene, that's C2H2, given the following thermodynamic data at 298.15 Kelvin, that's 25 degrees Celsius. So the first thing I want you to do is I want you to try to write a balanced chemical equation for the combustion of acetylene. You know that we have acetylene torches and they're super hot. Okay? Alright, so pause that video, balance that equation, and then restart it once you have balanced it. Bam! There's the balanced equation for acetylene. That's 2 moles of acetylene gas plus 5 moles of oxygen gas yields 4 moles of carbon dioxide gas and 2 moles of water vapor. Notice that there are 7 moles of gas on the reactant side and 6 moles of gas on the product side. That should tell you some information right there. Okay, here's that thermodynamic data from the data table here that I told you about. Now, I want you to take a look at the data in which you have. The data in which I have are delta H naught of formation, kilojoules per mole, and S naught at joules per Kelvin mole. Notice that the units are vastly different, but yet a little bit similar, okay, with the enthalpy and the entropy terms. We've got to be very, very careful with that. And we're going to calculate the delta G naught for this reaction using this data table. We don't have the delta G naught of formation, so therefore we can't use that. Okay, so what are we going to do? We're going to do this calculation. That is, the delta G naught for the reaction is equal to the delta G naught for the system is equal to delta H minus T delta S. It's the same thing that we've been doing before. Now, delta H naught for the reaction is products minus reactants. We've done this here before, and we have the temperature, that's 298.15, that's 25 degrees Celsius. And we also know how to do the delta S naught for the system. That's also NPR, products minus reactants. Therefore, that's why we're using that data table. So we're going to do this in a few different parts. We're going to calculate the enthalpy and we're going to calculate the entropy for the system, plug that in with the temperature, and then solve for the delta G. All right, so delta H, that is the enthalpy term. That's products minus reactants. We're going to plug in these values right into here. So delta H naught for the system is 4 moles of carbon dioxide times negative 393.5 kilojoules per mole plus 2 moles of water vapor times negative 241.8 kilojoules per mole minus the quantity of 2 moles of acetylene times 226.7 kilojoules per mole plus 5 moles of oxygen times 0. Again, elements in their standard state have enthalpy terms of 0. We're going to sum all this up and we're going to get a value of delta H naught for the system as equal to negative 2,511.0 kilojoules. So we're going to divide this by 2 moles of acetylene, excuse me, because the stoichiometric coefficient on the acetylene is a 2, and if you go back to that equation, if you go back to the question of the problem, we're going to determine the delta H naught for the combustion of 1 mole of acetylene. Okay, and so we're going to divide that enthalpy term by 2, and then we're going to get this value at negative 1,255.5 kilojoules for the enthalpy. Now, this is an exothermic reaction because this value is negative. Of course it's exothermic. All combustion reactions are exothermic. Think about that. Okay? Now we're going to calculate the delta S naught for the reaction. It's products minus reactants. We're using that data table. So we're going to plug that right in here, and that's what we've done. So the delta S naught for the system is the 4 moles of the carbon dioxide times 213.6 joules per Kelvin mole plus 2 moles of water at 188.7 joules per Kelvin mole minus the quantity of 2 moles of acetylene times 200.9 joules per Kelvin mole, plus 5 moles of oxygen times 205.0 joules per Kelvin mole. When I sum all this up, we're going to get this value for the delta S naught for the system at negative 195.0 joules per Kelvin. We also have to divide this by 2 because I have 2 moles of acetylene, which is coming from that balanced equation. And the question is asking for the delta H naught the delta G naught for the reaction of 1 mole. So this will also, I need to convert units from the joules to the kilojoules so I can sum up the enthalpy and entropy terms. I'm going to get negative 0.0975 kilojoules per Kelvin. Okay, this means it's more ordered. Now, this value is very, very, very close to not being negative. It's very close to being positive. And so you should also see that it's more ordered because as I aforementioned in this problem, we have 7 moles of gas on the reactant side and 6 moles of gas on the product side. So this is very close to being disordered, but it does matter on the temperature here in just a little bit. Okay, so it's very small on the ordered portion. So the entropy is more ordered, unusual for any combustion reaction. Okay, now we're not done yet because we have only calculated the enthalpy and the entropy terms. So what we need to do is plug into this equation, which is delta G naught for the reaction is equal to delta H minus T delta S. We're going to do that here on this next slide. Bam. Okay, so I've left in my delta H naught for the system there and the delta S naught for the system right there as well. I've left in both of those values as we calculated on the previous slide so that you don't forget about it. Okay? Here's the equation that we're plugging into, and that's delta G is equal to delta H minus T delta S. I love this equation. Super cool. Here is my delta H term. Okay, here is my T term, and here is my delta S term. Notice that my units are going to cancel here because I've already done that conversion with the entropy term going from joules to kilojoules. Okay, and the Kelvin temperatures are going to cancel out with my Kelvin temperature. That's a duh, hopefully. I plug this in here to get my delta G naught for the reaction. That's negative 1,255.5 kilojoules minus the 298.15 times the negative 0.0975 kilojoules per Kelvin. The kelvins cancels out. I'm left with kilojoules for both the entropy and the enthalpy terms, and this is the value that I'm going to get. So this is negative, so the Gibbs free energy, the available energy to do useful work, is negative 1,226.4 kilojoules with the combustion of 1 mole of acetylene at 25 degrees Celsius. Okay? So this is a spontaneous reaction as the negative sign on the Gibbs free energy indicates. Okay? The reaction is enthalpy driven. That's the delta H term because it is exothermic despite the negative entropy term. That negative entropy term is meaning that that is more ordered. So the product side is more ordered than the reactant side. All right, hopefully that makes sense to you. We're not done. We got a lot more to do on this particular problem. We got a couple of changes here. Now, notice I've made one very small change here. Okay, so I'm going to read the question here. It says, determine the delta G naught for the combustion of 1 mole of acetylene C2H2 given the following thermodynamic data at 15,000 degrees Celsius. That's the difference here between this problem and the 25 degrees Celsius on the previous problem. So I'm going to plug into the same equation here. Okay, delta G naught is equal to delta H minus T delta S. Okay, I got my delta H term right there. I've got my T term right there, which I need to convert into Kelvin. Simple process. It's just a little bit larger than that, not much more. And then I've got my S term right there. I plug these values in here. Hopefully you can see that. And delta G naught is equal to negative 1,255.5 kilojoules minus the 15,273.15 Kelvin times the negative 0.0975 kilojoules per Kelvin. The Kelvin units cancel out, the kilojoule terms sum up, and I'm going to get a value. This value is delta G naught for the reaction is 233.6 kilojoules. Okay, so you should see that this reaction is very different than calculation number 2. Calculation number 2, which is exactly opposite this one. Okay, calculation number 2, at elevated temperatures, boom, it switched that term over. Okay, so this reaction is non-spontaneous. Given the positive delta G naught for the reaction, this reaction is entropy driven despite the negative enthalpy component, which is of course exothermic. Okay, all right, still not done. We got more to do. Okay, we're going to graph that previous information that we just had there. Okay, we're going to assume that the change in enthalpy and the change in entropy are independent of temperature. Then the Gibbs free energy is a function of temperature. So let's graph that right here. So on the y-axis, I got Gibbs free energy. And on the x-axis, I got Kelvin in temperature. Okay, I've got my 2 points that I graphed before, that I just calculated rather, as the 2 blue dots, and I've drawn a black line in between those to indicate my line. Delta H and delta S are both negative. Okay, here is my point here, and here is my point here, my ordered pair of the Gibbs free energy and temperature respectively. Okay, the delta G equals delta H minus T delta S, that's my equation. Okay, we have reworked this here to come up with the Y equals mx plus b format. Okay, and then from this, we're going to find out what is the y-intercept. So we need to extrapolate this line. Not very much, but we need to extrapolate this line until it hits the y-axis. You can see that with the red little tiny dot that I've drawn there, and it's actually continued on up to the right. Okay, the intersection here is the delta H, as you can see in the y equals mx plus b format. Okay, and what is the slope? Well, the slope is the negative delta S, as you can see in the y equals mx plus b format. Okay, this is a positive slope here. So at equilibrium, delta G is equal to 0. That's where that blue line here. Okay, so above this blue line is when the delta G is positive and non-spontaneous. Okay, as you can see at that elevated temperature. Okay, below the blue line, it's spontaneous and the delta G naught is negative, and that is less than 0. Okay, so what is T star? That is the switch at which the temperature goes from either spontaneous to non-spontaneous in this particular case, or non-spontaneous to spontaneous, doesn't really matter. But that temperature gives you the switch. When does the switch occur? The switch occurs at delta G equals 0, which is at equilibrium. Equilibrium is defined at 0 for delta G. So that's when that switch of the temperature occurs. So let's solve this mathematically. Okay, T star is the temperature at which the switch occurs between spontaneous and non-spontaneous, or non-spontaneous and spontaneous. So we're going to solve for T star. We got our equation delta G naught is equal to delta H minus T star delta S. We're going to rearrange this, knowing that at Gibbs free energy, when Gibbs free energy is 0, we're at equilibrium. That's when that switch occurs. So we're going to substitute in 0 for delta G. So I've got delta G as 0. Now I got delta 0 is equal to delta H minus T star delta S. We're going to rearrange this, subtract delta H on both sides, then divide by negative delta S on both sides. The negative signs cancel each other out, and then we're going to have our T star is equal to delta H over delta S. We're going to substitute in here our values that we need here, and so the delta H term is negative 1,255.5 kilojoules, and I've converted my delta S into the kilojoules per Kelvin. That's negative 0.0975 kilojoules per Kelvin. I'm going to do the math on this, and I'm going to get 12,877 Kelvin. So notice that this value corresponds to the intersection point on the graph where it crosses the x-axis. So this is the temperature at which the switch occurs from spontaneous to non-spontaneous, or non-spontaneous to spontaneous. Okay? Hopefully that worked out really well for you. That's a really cool problem. Okay? Here's a little bit of humor that ties in with this unit. So this is super cool. Wait, what did you say? Do you have a question? Because you don't seem to give it. Maybe your delta G is at 0 and you're just ready for that switch. Hopefully you go for a delta G that's negative so that you can have a spontaneous reaction here. Spontaneous reactions are product favored and you're going towards the products, and I hope you're getting better and better at these chemistry problems. I am the Crazy Hat Chemist, and of course, we gotta have a crazy hat. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Please pass on my YouTube channel to anybody that needs chemistry help. Okay? You can get a cool sticker. You can get a t-shirt, and it has a back to it. Oh yeah. Gotta love the t-shirt. Have a great day. I'll see you next time. Bye for now.